Hello everyone, I'm Jiaheng Liu from Tohoku University. Now, I'm going to present our work, a conflict-aware capacity control mechanism for last-level cache. This is the outline of the presentation. First, I'm going to talk about the background and motivation of our work. Next, I will introduce our method. After that, I'm going to talk about the evaluations of our method and show conclusions in the end. As the number of cores in one processor increases, the number of cache levels and cache capacity increases sharply. For example, the level 2, which is last level cache capacity of Intel Pentium Pro in 1995, was only 256 kilobytes. However, the IBM Z15 system has a cache hierarchy with a level 3 cache of 256 MB and a level 4 cache of 960 MB. Meanwhile, leakage power increases with the transistor scaling, as well as the cache capacity increase. At the transistor level, FinFET has been developed to replace the classical CMOS to significantly reduce the leakage power. However, the growth trend of the cache leakage power is still exponential as the cache capacity increases. Therefore, deeper and larger cache hierarchies can have a significant impact on performance, but they will consume more energy. This motivates many studies to focus on cache reconfigurations. The cache usage behaviors of individual applications can be very different. As this figure shows, not all applications require a large cache capacity. For those applications, using the large cache will increase power consumption without contribution to performance. Based on that, many architectural studies have improved the energy efficiency by cache reconfigurations for individual applications, including selective cache weights, cache associativity adjustment, multiple level bypassing, and so on. But these studies still have some disadvantages. Besides, distinguishing different kinds of cache misses is also helpful for cache reconfiguration. The motivation of this work is to improve the energy efficiency of a computer system with a deep cache hierarchy by adjusting the cache configuration based on the cache usage behaviors, which including cache capacity demand and associativity demand of individual applications. Next, I'm going to introduce our method. The procedure of the method consists of two main steps. The first step is the cache level bypassing. This step aims to select an appropriate cache hierarchy in a cache level granularity that achieves a high energy efficiency of the computer system. In this work, the cache level bypassing is achieved by the multiple layer bypass mechanism. Only level 3 and level 4 caches are considered in cache level bypassing because energy consumption of level 1 and level 2 caches are not significant. After the configuration of a cache hierarchy is decided at the first step, a conflict-aware capacity control is performed. This step aims to select the appropriate cache capacity and associativity of the last level cache to keep the performance impact of last level cache misses insignificant. It can also be divided into two parts. As the control flow for the last level cache control mechanism shows, the left part is for the capacity decision. After this part, the mechanism chooses the last level cache capacity to be checked. Then, the right part, which is for associativity decision, checks whether last level cache misses are mainly contributed by capacity misses or conflict misses, and generates the final configuration. In the next slide, I will introduce both parts in this step. The first part is called capacity judgment. In this part, we track the number of misses in the last level cache with the current activated with, and use a capacity demand quantifying metric, last level cache miss per kilo instruction, and a threshold Tm to judge and decide the capacity. If last level cache miss per kilo instruction is smaller than Tm, some cache width can be disabled. Otherwise, no cache width can be further disabled. The second part is called miss imbalance judgment. The cache set miss imbalance occurs when cache misses concentrate on a particular subgroup of total cache sets. Therefore, we track the number of misses in each last level cache set and use the metric CV, which is coefficient of variation of last level cache set misses, and the threshold TCV to quantify last level cache miss imbalance and decide the associativity. If CV is larger than TCV, our mechanism judges that significant cache set miss imbalance occurs and doubles the associativity of the last level cache to reduce conflict misses. Here are two examples to help you understand how the mechanism works. For both examples, last level cache miss per kilo instruction is larger than Tm when half of weights are disabled in the last level cache. In the first example, CV is larger than TCV. Therefore, our mechanism doubles the associativity of the last level cache to reduce conflict misses. After confirm that last level cache miss per kilo instruction is smaller than Tm, the final configuration is decided. In the second example, CV is smaller than TCV. Cache misses are mainly caused by the small cache capacity. Therefore, the mechanism selects the former last level cache configuration of the capacity and associativity as the final. To evaluate our method, we use the Sniper 7.2 simulator, which has been validated in real systems and can simulate various applications running on different cache hierarchies, and the Parsec benchmark suite for performance evaluation. The specifications of the baseline system and the simulation parameters are listed in the slide. We have decided the simulation parameters basically assuming Xeon X5550 processor. This table shows the cache hierarchies and last level cache associativity selected by the cache level bypassing and proposed mechanisms. From the results, we can see that even after bypassing a cache level, the applications underutilize the last level cache capacity, and thus some of last level cache widths are disabled by the proposed mechanism. For retrace and swaptions, the proposal can remedy the non-optimal cache hierarchy selected by the cache level bypassing mechanism from the final configuration results. For swaptions, black skulls, and body track, the associativities indicate that, in some benchmarks, the last level cache associativity is increased to reduce the conflict misses induced by decreasing the cache capacity. Energy efficiency is defined as the number of instructions per cycle divided by energy consumption. The figure shows the effects of the proposed mechanism on energy efficiency. The proposal improves energy efficiency by 26% and 10% on average over the baseline and cache level bypassing mechanisms, respectively. From the results of IPC and energy, we can observe that at the sacrifice of small performance degradation, energy consumption is significantly reduced due to the energy saving by bypassing and powering off a cache level and also decreasing the last level cache capacity. Some applications can achieve slight IPC improvement by our mechanism because of the conflict misses reduction in the last level cache. We also show the CV and the number of last level cache misses before and after associativity adjustment for some applications. In this figure, the baseline of the normalized number of last level cache misses for each benchmark is the number of last level cache misses before associativity adjustment. As the CV decreased by associativity adjustment, the number of last level cache misses also decreases due to fewer conflict misses. This result proves that the metric CV can effectively represent the conflict misses in the last level cache. In this paper, we have proposed a conflict-aware capacity control mechanism focusing on the energy efficiency of a cache hierarchy. The mechanism determines the last level cache capacity and associativity by measuring miss per kilo instruction and set misses imbalance of the last level cache respectively. It achieves significant energy saving at the sacrifice of small performance degradation. The proposed mechanism has been evaluated with benchmarks from the Parsec benchmark suite on a multi-core simulator. The energy efficiency improvement are up to 26% and 10% on average, compared with the baseline and the cache level bypassing mechanisms, respectively. In the future, we will investigate our mechanism with other benchmark suits, multi-programmed workloads, and newer technology. We will also extend the mechanism to an online version and investigate its overhead. In addition, the connection between its mechanism and cache partitioning will also be considered in the future. Thank you for your listening.